Thank you very much. And hello, everyone. I'm Felix Suchert from TU Dresden, and I want to present our work on STEMP Rust, a language and performance comparison to see on transactional benchmarks. Well, so software transactional memory has been established as a method for state synchronization for over 20 years now. But as recent research has shown, it is still very relevant today. But the main problem is that most of the frameworks have been written using the C programming language, which is notoriously unsafe and should therefore maybe be replaced with a more safe programming language. So the question that we asked ourselves in this work was whether or not the Rust programming language, which is often dubbed the rising star in the system programming community, could be used as a replacement in transactional memory applications. So Rust's key promises focus on safety and performance. And so the question that we want to answer is whether those two promises can hold true in a transactional environment. For our work, we looked at the STEMP benchmark suite, which is also a very established benchmarking suite that has been around for more than 10 years by now. And to start things off, we automatically translated those benchmarks, which are originally written in C, using a tool called C2Rust into the Rust programming language. You can see an excerpt of the code on the right-hand side of the slides. And for those of you that are a bit well-versed in Rust already, you probably already see that the quality and the safety of the code is very questionable. You can see the unsafe keyword in line number 1 that already indicates that the body of this function already abandons most of the safeguards that Rust is putting into place. You can, for instance, see on lines 7 and 9 that raw pointers are being dereferenced, pointer types are being cast between different types, which is also considered unsafe behavior because the Rust compiler cannot verify the correctness of such operations. Moreover, we also see that manual memory management is happening in the form of malloc and free calls, as you can, for instance, see on lines 11 to 13, where memory is manually allocated, which is also not considered safe behavior in Rust. And finally, the code that is generated automatically is also not very idiomatic and therefore very hard to maintain. As a result of this not very promising outcome, we decided to also implement the benchmarks from the STEMP suite ourselves in Rust by using better programming patterns that are endorsed by the Rust programming community. And while we translated those benchmarks, we observed a number of problems or patterns in the original code that are very problematic and cannot be used in Rust as they are because they are also unsafe. I'm now going to present them and also shed some light on the potential overhead this safety will incur. The first pattern is parallel access to shared state. And as a running example, I want to use the SSCA2 application, which is part of the STEMP benchmark suite. And what this application does is it constructs a directed multi-level graph by using different auxiliary and adjacency arrays that are all computed on in parallel. And what happens in this application and many others from the suite is that those arrays are just accessed in parallel, and safety is only ensured by partitioning the set of indices to ensure that no overlaps happen. This is, of course, very error prone, and since developers cannot exactly be trusted with the safety of a program, Rust forbids such mutable data sharing between different threads. So what we had to do when we ported the benchmarks was to split those arrays into multiple smaller arrays, which could then be assigned to individual threads to work on. But of course, this incurs a lot of overhead because more allocations need to be done to allocate memory for those new smaller arrays, and also a lot of data movement overhead is incurred by not only moving the data from the large array to the smaller ones, but also by moving those smaller arrays into the different thread scopes. Another pattern that is somewhat related to that we encountered was the use of specialized data structures in the C version. This is most prominently seen in associative data structures such as hash maps and hash sets, which have been altered to be some sort of transaction aware, so that those data structures could be used within transactions more efficiently, which helps to boost the performance of the C implementations. Another problematic pattern that we encountered was the violation of the transactional model itself. Since the C implementation has no type guardings, the transactional functions that are used to access different values are mere wrapper functions. And what we see, for instance, in the SSCA2 benchmark is that frequently the application shifts between a transactionally parallel mode to a data parallel mode, where those transactional wrappers are just discarded, which would incur a lot of overhead if they were used. And instead, values are accessed directly, which is, of course, also very unsafe because it relies again on the programmer to know when the transactional mode is happening and when such a data parallel mode is happening. Therefore, the Rust type system here also helps to enforce more safety by encapsulating the value that should be accessed in a transaction behind such a transactional API, which then prohibits any access to the value directly. This, of course, again, leads to more overhead because each read that is performed on such a transactional variable incurs duplication of the data, as data has to be copied out of the transactional value into the rest of the program to be bound as a local variable. And this is especially costly when such an access should happen outside of the parallel context, as can happen very often, especially in the stamp benchmarks. And every time this happens outside of the parallel context, the overhead becomes even worse since the execution happens sequentially. But on the other hand side, this safety allows also for the safe composition of transactions, which was a problem that has not been solved in the TL2 benchmark, in the TL2 transaction library, which is the version that C uses. In the Rust version of the transactional library, we have a transaction context, which you can see here in the function argument list. And the presence of such a transaction context in any function argument list would then indicate to the developer that this function has to be executed in a transactional context, and therefore this helps to improve also the safety while writing the code already. To take a look at the results, so besides the original C-based implementations that we already had, we obtained a automatically translated version using C to Rust and implemented a manual version of the benchmarks using the Rust STM library. We then measured the speed up over a sequential implementation, and those are the results. Here I show the results for 12 threads, but you can obtain more measurement points from the paper. And one point that we can see very easily is that Rust STM, pictured in orange here, is often significantly slower because it has to adhere to all the safety rules and safeguards that Rust puts into place. While we can see at the same time that the Rust TL2 and the CTL2 versions perform very good because they don't have to adhere to those safety standards. So when we come back to the question of whether or not the promises of the Rust programming language can also hold up in a transactional context, we see that in terms of safety, Rust indeed helps to improve the quality of the code and also the safety of the code at runtime. But we also see that the speed can only hold up to the C version when we are using unsafe code. This in the end is, of course, mostly due to the unsafe behavior that the TL2 version of the C benchmarks uses. But still, overall, we see the performance takes a bit of a hit here when we want to rely on more safety. Okay, this was it for my talk. Thank you very much also for your attention, and feel now free to ask any questions if you have any.